Hello and welcome to the segment of the video that is going to cover the material for Chapter 16 on the third exam of the semester in General Chemistry 2, CHM 136 here at York College. The first question that we'll be covering, depending how they're numbered on the sheet, but the first question relating to Chapter 16 is about a buffer solution, the mass of lithium hypochlorite that we need to prepare a particular pH in a buffer. So find that question and we're ready to get started. Alright, so anytime we make a buffer, it's helpful to start with the Henderson-Hasselbalch equation that tells us the pH of that buffer is equal to the pKa of the acidic component of the buffer plus the log of, and then this ratio would be the ratio of the concentrations of the basic and acidic pieces of the buffer. So we're going to use this equation first to find out the concentration of the base, and then the stoichiometry would allow us to find the mass of the base. So we're interested in a pH of 7 as our final pH. The pKa would be the negative log of the Ka, which is provided 3.5 times 10 to the negative 8, plus the log of unknown concentration of the base, and then our acid is 0.2 molar. So first we have to do a little bit of algebra. So the negative log of 3.5 times 10 to the negative 8 is 7.46 plus the log of this base concentration over 0.2. So when we subtract, we've got negative 0.46 equals the log. And we must raise both sides 10 to the x power. So the ratio, our base divided by our acid concentration, is this 0.347. So our base's concentration will simply be 0.0693 molar. And that's our lithium hypochlorite. Now, to go to the mass, we need to now know how much solution we're preparing, the volume, 0.1 liters. And then we're going to need the molar mass of lithium hypochlorite. So if we take our 0.0693 moles per liter of LiClO times its molar mass, we would add together lithium 6.941, chlorine 35.453, and oxygen 16. Times 58.394 grams per 1 mole. And then if we multiply by the 0.1 liters, we'll see that we get the mass of lithium hypochlorite. So we should need 0.405 or 0.41 grams of lithium hypochlorite. Okay. All right, our next question. Again, a buffer. What is the pH of an aqueous solution containing? And we see a conjugate pair. We're told we have 0.5 molar carbonate ion and 0.2 molar bicarbonate, HCO3 minus. Anytime we have a pair, conjugate pair, again, the pH comes from the Henderson-Hasselbalch equation. In this case, the basic piece is the carbonate, and the acidic piece is the bicarbonate. So what we need is the pKa. Now we're given some sneaky information here. We're given that the Kb of CO3 minus equals 2.1 times 10 to the negative 4. The conjugate partner, though, HCO3 1 minus, would have a Ka such that the product of these two is Kw, remember. Ka times Kb for a conjugate pair are equal to Kw. So the Ka of our HCO3 is simply going to be Kw divided by Kb. That's 1 times 10 to the negative 14 divided by the 2.1 times 10 to the negative 4. So it's 4.8 times 10 to the negative 11. We can then use that to find our final pH. Alternatively, by the way, we could have calculated the pKb of carbonate and then subtracted from 14 just to get the pKa. So you have a couple of options. Now what we need to do is, in the log, put the base part, 0.5, in the numerator, and the acidic part, 0.2, in the denominator. This is 10.32 plus 0.40, so that should be 10.72, the pH of this buffer solution. In question 14, which of the following combinations is best to make a buffer of pH 5? So again, the pH is strongly tied to the choice of acid in a buffer. So the first thing we want to do is look at the Kas and thus the pKas of the materials available. And so knowing a little bit about logarithms, the power of 10 in the Ka is pretty close to, or is only 1 away, if you look in both of these cases, from the log value of it. Look, it was 10 to the negative 8 and a 7 here, and 10 to the negative 11 and a 10 here. So we can sort of save some time rather than calculating all these. To get a pH of 5, the 1.8 times 10 to the negative 4, or 5 Ka in C, which has the acid, acetic acid, CH3CO2H, that's going to give us the pKa as close as we can get to a value of 5. 4.74. So we would elect to use selection C in this case to get us as close as possible with a starting value, at least, just by choosing this acid to work with. 15, or the next question, sorry, might not be number 15, but each of the following mixtures can produce an effective buffer solution except. So the rules for buffers, again, are that you have a weak conjugate acid-base pair. So you need two materials that are related, that are different from each other only by a proton, a single hydrogen. Okay, and it needs to be a weak acid. So in selection A, they are related, but the acid is strong. So that cannot function as a buffer, actually. So we already have the answer for this question, that A. But just to confirm, B, HF is a weak acid, NaF, F minus is its conjugate base. C, we see this buffer actually that we worked with earlier, HCO3 minus from the Na, HCO3 minus. Again, you have to ignore your spectator ions, your sodiums, potassiums, lithium in this earlier case that we did. But anyway, you'd have HCO3 and CO3 minus 2, that's a conjugate pair. In D, HPO4, 2 minus, and PO4, 3 minus, that's a conjugate pair. And in E, NH4 plus, NH3, that's a conjugate pair of a weak acid and conjugate base. All right, let's move on to some other questions. Another buffer question involving now ammonium, actually that one we just mentioned, NH3, NH4. So what is the pH when we dissolve 4 grams of ammonia, 8 grams of ammonium chloride in half a liter of water? So this is all about the stoichiometry. We need to take our 4 grams of NH3 and our 8 grams NH4Cl and convert each of these to moles. For NH3, its molar mass is about 17.03. For NH4Cl, it's about 53.49. So we have 0.235 moles of NH3. And 0.150 moles of NH4Cl. More importantly, though, of the NH4. Here the Cl is the spectator ion. So our pH will be the pKa plus the log of the concentration of the base, which in this case is the ammonia. It has fewer hydrogens on it over the acid NH4 plus. The acid always has the additional hydrogens on it. So we're given the Ka of ammonia, negative log of 5.6 times 10 to the negative 10, plus the log of. Now normally we would convert these two to concentrations. Let's go ahead and do that. But we can actually save ourselves a touch of time here because the ratio of these two numbers, 0.235, 0.15, will be the same when we divide each by the same value. Okay? If you had $100 and a friend of yours had $50, you have twice as much. But if I take half from each of you, you end up with 50 and your friend ends up with 25, you still have twice as much. The ratio has remained the same when I divided you by the same quantity here. Nevertheless, this would become a 0.47 molar, and this would become 0.3 molar. So we can put those concentrations in, 0.47 and 0.3 molar. Our pKa is 9.25. It's going to be plus. Because the base is higher, I know that's going to be a positive value. 0.19. So we're at 9.44 as the pH of this buffer. See, that is different from the answer that I provided on the answer sheet. So I want to just double check my math real quick to make sure that the solution that we have right here, and I can see the answer on the answer sheet subtracts this value right here. That is a mistake on the answer sheet. This is the correct value because the base is the higher concentration. Base raises the pH, so logically it makes sense that our pH should be higher than our pKa. So I'm confident that the 9.44 is the answer, not the 9.06 shown on the answer, the solutions set. All right, let's move on to the next question, which involves a titration, very similar to a buffer. In this titration, 25 milliliters of hypochlorous acid are titrated with sodium hydroxide. What is the pH when 85% of the acid is titrated? So our reaction is weak acid, HClO, plus the strong base, NaOH, but it's really the OH that's important. This will be a complete forward reaction due to the strength of the strong base. This will make ClO- and water. we will set up a reaction table in moles. That is our policy anytime we anytime that we are doing a forward reaction, we want to work in moles. Then we add a fourth row down here to figure out the concentrations. So our moles of acid come from taking the molarity of the acid that we're working with, 0.2 times the 25 milliliters. So we have 0.0050, right? Molarity times volume is moles. Now the 85%, so all we need to do is multiply this number by 0.85, and that is how many moles of OH we are adding. That's what the question says, when 85% of the acid is titrated. Okay. Now, that's actually a little bit of a sneaky thing here, because now we have to use this up here for our OH minus, the 0.00425 moles, okay, divided by some unknown volume, equal the molarity, the 0.25 molar. So I'm going to solve for the volume of NaOH that we've added. The volume will be the 0.00425 divided by this 0.25, or 0.017 liters, 17 milliliters. That's an important number because I need to add that to the 25 milliliters of acid that I started with. So the 25 plus the 17 is 42, or 0.042 liters. I'll need that a little bit later. Okay? Often we're told the volume of base that we're added. Here we were told conceptually how much base was added relative to the amount of acid. Now we look at this problem, and this is a case where we're looking at a limiting reactant, right? We have a complete reaction because of the strength of the base. And so this reaction will occur until one of these reactants runs out. We have no hypochlorite at the start. So the smaller number is the hydroxide. So we will subtract it from each reactant and add it to the product side. So there won't be any hydroxide left. And there will be a small amount, 0.00075 moles of HClO. And then, of course, 0.00425 on the product side. Now, when we divide each of these moles by this total volume, we'll get the concentration. 0.0179. And 0.101. This is a conjugate pair, an HA, A minus pair. So we can go to the Henderson-Hasselbalch equation. Negative log of the Ka, which is given 3.5 times 10 to the negative 8, plus the log of our base, 0.101, divided by our acid, 0.179. And I come up with a pH of 8.21. Let's move on to the next one. Another titration, but this time we are titrating a weak base with a strong acid. This first titration that we did was a weak acid with a strong base. Now we are titrating in our next question ammonia, NH3, with HCl. So that's essentially H3O plus, because all of these dissociate and the H's bond to waters. This will produce NH4 plus and water. Again, we'll work our table in moles. And add our concentration row at the end. So this time, 25 milliliters of our ammonia, so 0.025 liters times 0.02 molar. It's 5 times 10 to the minus 4 moles. And then our strong acid, 28.2 milliliters times 0.01 molar, 2.82 times 10 to the minus 4. This is the limiting quantity, so it becomes the limiting reactant and the amount by which we change. So we'll have 2.18 times 10 to the minus 4 moles of ammonia left. And we will have formed 2.82 times 10 to the minus 4 moles of ammonium in this case. All right. Now, we would calculate our concentration. So when we mix the 25 milliliters of ammonia with the 28.2, that's going to give us 53.2 milliliters. So our ammonia concentration is 0.0041, and our ammonium chloride concentration is 0.0053. Okay, the pH again will come from the Henderson-Hasselbalch equation. We could look it up earlier on our chart, but just to follow what the problem is intending us to do here, we're given the Kb of ammonia. So I'm going to calculate from the Kb, which is 1.8 times 10 to the negative 5. Again, I'm going to calculate the pKb. .74. So the pKa of ammonium, the conjugate partner, will just be 14 minus that value, or 9.26. So now I can take 9.26 plus the log of ammonia is our base, 0041, over ammonium, 0053, our acid. And we end up with 9.14 as our pH for this titration. Okay. All right, we have one more titration question here. milliliter sample of ammonia with aqueous HCl. What's the pH after 15 milliliters of this? So it's the same reaction, so let me go ahead and just erase these numbers. This time we're beginning with 50 milliliters of 0.024. So we have 0.0012 moles of ammonia, and we have HCl 15 milliliters times 0.06 molar, so 0.0009 moles. So again, the strong component is the limiting reactant. We'll have none of that left. We'll have 0.000. Well, for zeros there, catching myself. 3.0009 moles there. In this case, our total volume is 50 and 15, 65 milliliters. Over here on the product side, that's going to be 0.0138 On the reactant side, it's going to be 0.0046. Once again, we can come down here to our Henderson-Hasselbalch equation. We can still use the same pKa. We just need to put our concentrations in the right place. 0.0046 over 0.0138. And our pH drops to 8.78 in this titration. Okay, sorry to go through that one a little more quickly, but it was the exact same reaction, so it was just starting with a different set of numbers there. All right, let's turn our attention to these KSP problems now. The solubility of lead chloride is 4.4 grams per liter. What is the value of KSP? So lead chloride, PbCl2, will dissociate into lead and 2 chlorine minuses. So the amount that dissociates, that is the solubility, in other words, the minus X, so to speak, will populate these sides over here, okay? But we'll have plus X and plus 2X. So these will be X and 2X. But we can actually figure out what the X is, because that is the solubility of the lead chloride. So the 4.4 grams per liter, all we need to do is convert this to moles per liter by dividing by the molar mass of lead 2 chloride. So we get our periodic table, add together lead, which is 207.2, and 2 chlorines. It's pretty heavy, 278.11 grams. So we're looking at 0.0158 moles per liter that actually dissolve. Therefore, our concentration of lead will be 0.0158 molar, and our concentration of chloride ion will be double that, 0.0316 molar. Now the KSP is the concentration of the lead times the concentration of the chlorine squared, because its coefficient is 2. So we just need to plug these values in now. 0.0158, 0.0316 squared. And the KSP is 1.6 times 10 to the negative 5. Our next question is also KSP, this time going in the reverse direction. We're given the KSP, so what is the concentration of bromine ions for lead bromide? So again, PbBr2, this time would dissociate into lead and 2 bromine ions. Some amount of this lead bromide will dissolve, producing equal and then twice as much that amount in bromide. So the bromide ion will be 2x. Now this time we don't have any information about how much dissolves like we did over here. We're actually trying to figure that out. So our KSP will equal the lead concentration times the bromine concentration squared. So that's x times 2x squared, or 4x cubed. The KSP is given as 6.6 times 10 to the negative 6th power. So we can divide by 4. And then we would take the cube root. And x is 0.0118 molar. Now, X does not represent the bromine concentration. That would be the lead concentration. But the bromine concentration is 2X as defined in our reaction table. So we just need to double this answer, and that is 0.0236 or 0.024 molar. Okay. One more KSP question. What is the solubility of silver chromate in a solution of potassium chromate? So here we have the common ion effect in play. Our salt of interest is the silver chromate, Ag2CrO4. It would produce 2 units of silver and the chromate, CrO4 2- ion. So we're interested in what is the molar solubility. Very similar to this problem that we just solved right here. In other words, how much of the silver chromate is going to dissolve? We don't know that. But in this case, we're not beginning with empty water, just pure water. Here we have 0.005 molar chromate ion. That's coming from this K2CrO4 solution. So there's 1 unit of chromate per every molecule of potassium chromate. So the concentration tracks 1 to 1. Beginning with 0 silver, under silver would be plus 2X and plus X. So 2X for silver, but the effect here of the common ion being present is that the equilibrium will be decreased. We won't be able to come as far to the product side because we already have a certain amount of chromate ion here. So this reaction will be limited in how much additional chromate it can make. So we might as well ignore the tiny bit of X that will be added to it. So our KSP expression, which is silver squared times chromate, will become simplified though. KSP is 5.4 times 10 to the negative 12, 2X squared times the 0.0050. So we would divide the 0.005, 5.4 times 10 to the negative 12, divided by the 0.005. Lots of ways we can do this, but this side's going to be 4x squared. This side's 1.08 times 10 to the negative 9. I just chose to divide this over here. Now I divide by the 4, and then I would take the square root. If I divide by 4, it's 2.7 times 10 to the negative 10. And then when I take the square root, I get 1.6 times 10 to the negative 5. Now this does represent a molar solubility because it is the amount of silver chromate that will dissolve now in the potassium chromate solution that we have there. Okay. So that wraps up all the questions relating to Chapter 16. I hope you were able to follow along, even though I went through them fairly quickly. And if you have questions, feel free to follow up with me in class sometime.